Steve, I think it's about time. And let me pray before we start. Father, thank you for this day and thank you for the privilege to be here. As we try to learn something about pi, help us to just understand the concepts and also give you glory in everything that we see and do. We praise in Jesus' name. Amen.
Amen.
So, good afternoon. I think I'm assuming most of you are here this talk. So, in our first talk, we showed that Archimedes, how he approximated pi. What he did was he knew a circle, he can inscribe some other polygon. It could be square or any other shape, 6-sided, 8-sided, or any side. Then he can estimate, especially if you use regular polygon, you know how to find the circumference. So he was estimating it by inscribing a polygon and then maybe inscribing outside. Then he takes the average of the two. But then he figured out if I can insert more sides, if I can double the size from 8, for example, to 16, from 16 to 32, then he figured out I get closer to the perimeter from inside and from outside. That would give me a better approximation, and that's how he did it, and that's what I showed you last time. But today I'll show you also something that is more superior, but most of this really rely on his idea. But they had more access to modern mathematics, especially Newton, Euler. They knew exactly what they were expecting to do. And most of the work they did here, actually they didn't do it even to find pi, but on the way they discovered there is a way to discover pi, or at least they estimate pi, using series. So most of the things that I will show you is how we can use series to estimate pi. And the first one, and the second talk, the first one is I'll show you Newton's approximation. Then I'll show you also using infinite series. Newton's approximation was actually very ingenious. He relied on his integration, newfound integration, and then he showed I can use geometry also to estimate, so I can equate them together and I can find pi. But Euler, Vitus, and also Leibniz, they showed they can find series. And I'll talk a little bit about their history and why they did what they did. This is classical history. In most cases, you can find them in many textbooks, but you have to find historical books maybe. So the first one is Newton's approximation. Isaac Newton. What happened was in 1617, Newton found he can find pi accurately, and his method was simply he used the concepts of geometry, analytic geometry, which was calculus. It was new for him. He was the only one probably new, and maybe Leibniz at that moment in the 17th century. But Isaac Newton, he knew how to find the area, so he's trying to estimate pi, and he knew pi is somehow it has to do with circle. So what he did was he said, I'm going to consider this circle or semicircle having center at 1/2 and 0. So he describes the equation, and as you can see, the equation of the circle in here. I don't know if you can see the green one; it's very small back here. The center at 1/2 and 0. Center at 1/2 and 0. Then he solved for y, semicircle, the top semicircle. Let me show you the graph, what it looks like. So what he did was, this is the semicircle. So he knew the semicircle, but he wants only to find this area. And I mean, nobody knew how to find this area before him. They had estimates. Actually, Archimedes had some ways of finding area of sphere and cones, but he didn't tell us how he found them, except he told us this is the area. So they didn't have this type of graph, but Newton, he said, I'll consider the semicircle from just 0 to 1, that's what he did, and then I'll center that 1/2 and 0. So he described the circle's equation, y equals the square root of x minus x squared, or you can factor out the square root of x, and that's what he did. Next one, what he did was, well, he developed this binomial theorem that works also for fractions, not only for integers. Usually the one that they teach us, Pascal or other binomial theorem, it is, if you have an equation like x plus y quantity squared or power n, then you can use binomial expansion. Well, Newton actually, he found expansion, his generalized expansion. You could do also for powers of fractions, like 1/2 m over n, and so on. You can do that. You can do that. So what he did was he expanded this fraction by factoring out x from here. Then he expanded this 1 minus x to the 1/2. You can think that 1 plus negative x to the 1/2. Then he expanded it using his binomial theorem. So the expansion of this one is this one in terms of series. He knew that this is a series. So if I'm going to find the area of this shaded region, if I'm going to find this area using his own integral, he said I don't need to find the whole semicircle area, but just I can integrate from here to here to 1/4. And that's what he did. He integrated that part using this new series representation of the semicircle. So he integrated them. So the integral will be from 0 to 1/4, but he's using the series, so the integral is going to be series too, because term by term integration. He did integrate term by term here, and then he said, well, now I can estimate actually something from here, the area, but he knew that this area is this area that we are dealing, ABD, the shaded area that I showed you. He can estimate it using this one by integrating, but he can find it also using geometry. So this is a series, and we don't know, I mean, it should converge hopefully, but we don't know how to find the limit. There are infinitely many terms here. But in his idea, well, I can evaluate at 0, which would, every term would be 0 here, every term will be 0 because every term has x. Can you guys see? Every term has x, so it will be 0 at 0. But at 1/4, I can evaluate at 1/4, so it does evaluate at 1/4, and this is what you get the first few terms. 1, 2, 3, 4, 5, 6 terms. These are the first 6 terms, but Newton used the first 9 terms. And then, I don't know if he had calculator because they didn't have calculator, but he calculated them. He found all these 9 terms. That's what makes it very brilliant actually, because he didn't have access to technology like we do now. So he added these terms. I mean, 2 he divided by this number, and by that number subtracted, added, subtracted. So he used the first 9 terms, and then he found actually if I use the first 5 terms, the 9 terms, I would get that decimal approximation of that integral. The shaded area, he knew that it is 0.07677310678. That is the area that he found using his integration with 9 terms. In his case, he uses 9 terms. He can use more terms or less terms. He can use 5 terms to approximate, but he uses 9 terms. We're using his own. Then he figured out also that area actually I can find it also using geometry. I can find it using geometry because the area ABD by geometry, Newton first determines the area of the right triangle ABC. Let me go back to the triangle to show you. ABC would be this triangle A, B, and there's something wrong. I probably have it wrong. Not this triangle, that's what I meant to be. So it should be DBC in my notation. The triangle, he found that area, which would be simply right triangle, half times base times height. So that's what he did here. So notation wise this is incorrect, but the rest is I have DBC, okay. I don't know why I said ABD, but it's DBC on the correct one here. So the area of the DBC is half the measure of BC, BD, and so he used the given one because the length BD is in Pythagoras theorem, we can find it. And then the length is square root 3 over 4, then the area would be half times base times height. So he knew the area of the triangle to the right of the shaded area is square root of 3 times 32. He knew that. The next what he said was, well, I can find also the area of the sector. The sector being, let me show you, it's very hard to go back, but the whole sector. This sector, you can find this area. Then the only thing that he needs to do is, if he knows the whole area, minus whatever he found the area would be, the triangle area would be the shaded area. So if I can find the sector area, I can subtract the right triangle area, which I know how to find. He found it. Then it would give me the remaining shaded area, which means that's what the whole idea is. And here's what he did. He found the area of the triangle, square root 3 over 32. So he said, well, the area of the sector is 1/3 of the semicircle. He knows how to find semicircle because it's half of circle. Okay. So 1/3 of half circle of pi r squared, which is easier, and he found it's pi over 24. The semicircle has area pi over 24. If I subtract pi 24 minus the square root of the triangle, the sector, then it should give me the area of the shaded area. So he said, well, then I can put them equal. He has the estimation using his series, and then he has area using geometry, then say let's make them equal. And that's what he did. He makes them equal, and then that equals, they should be his area also. So his area is equal to the area that he found by geometry. They are approximately the same. They are not equal because we have decimal approximation that we have to worry, rounding errors. So he solved for pi, and pi is from here, 24 times that area plus that one, and then he found pi approximation. This one was done without calculator. And then this is actually about 7 digits placed correct with our known. We can verify them. The first 7 digits are about the same with our. And this might be the most accurate up to that moment, up to that point. Newton's was the best approximation of pi. But he is serious. Correct 7 decimal places. Before him, there were others that have found better approximation, but they used Archimedes just by doubling more sides inside or outside the circle. This would be the first one in its kind when Newton showed that. So this is one of them. The other approximations are, my favorite one is Euler's. Newton's is actually very clever because it was new in his time, but his was in 1734, Euler announced it actually, this was a Basel problem actually at the 17th century. This was a big problem in Europe. They knew the series 1 over n squared is convergent, but nobody knew where it converges. And they knew the series 1 over n is divergent, but they can show it using integral test, so they knew it was divergent, so there was no issue. But the question became, why is 1 over n squared converge, and if it converges, to what does it converge? So Euler worked on this one, and Euler found a method to show that, in fact, it converges, not only it converges to pi squared over 6. What is very interesting about this series is, if you see on the left side, 1 over n squared, everything is rational. Because n is integer, 1 over n squared is integer, rational. 1/4, 1/9, 1/16, all of them are rational. So you're adding infinite rational terms on one side. Then on the other side, pi squared showed up, which is a irrational number. So that was very striking for many of them. They said it can't be because the sum of infinitely many rationals should not be irrational because they didn't have. If we have finite terms, it would never happen. Sum of 2 rational is always rational. But for infinitely many, then they found out, okay, this is something is wrong. But Euler being smart, he showed them how he did it, and still it stands. In fact, whenever you see Euler's books or something, always they have this equation or his Euler formula, famous one, imposed on his picture, because these are still maybe the best inventions to our day. I don't know. You can always argue. But how did he do? Well, being Euler helps. He's smart. So what he did was he knew sine x has series representation. You guys know in Calc 2 they show you sine and cosine. They can be represented with series. For sine, you would have x minus x cubed over 3 factorial and so on and so on. You do that, and you do for cosine also by switching them. So what he said was, Euler said, if I can find a function that has polynomial type, it has many roots, n roots at least, or infinitely many roots, but like polynomial. Because if you have a polynomial with n roots, what do you do? X minus the first root times x times the second root times the third root, and so on. So if I could do that, maybe I can solve this as sine x over x. He did sine x over x, not sine x only. He found the sine series, then he divided it by x. So it would be 1 less power. And then he said, I can write sine x over x in the form of its roots. Well, sine has many roots. Sine x equals 0 has many roots. What are they? Multiples of pi. Pi, 2 pi, 3 pi, negative 2 pi, infinitely many of them. So what he said was, well, I could do that. So what he did was, the first root would be 1 minus, it would be x squared over something, but he used pi, but in our case, we changed it to pi over 2. Pi over 2, in his case, was x over x. So this is the expansion that he found himself, in terms of x, instead of pi over, he had x. So that's how he found it for the other one. But then he was working on this one and he said, well, maybe I can play also with pi over. He did it himself, Euler. I don't know what his intention was. So he said, well, instead of pi, I'll put pi over 2 here, pi over 2. So if I do that, I would get what I have here, this series. You can see the series representation. Well, on the top, you can simplify this one a little bit more. He simplified it. If I simplified it, on the right side, because sine pi over t is what? It's 1 over pi over 2. Sine pi over t is 1, so he gets on the left side. On the right side, if he simplifies them, the pi's will cancel by pi's because they have pi's on top and bottom, but the numbers, he found that that's what I would get. These are very interesting numbers, and then he simplifies them further by subtracting from 1, 1/4, he will get 3/4. Subtracting 1/6 from 1, he gets 15 out of 16, and then he knew that, oh, I can rewrite it actually in terms of this one. On the top, I'll have 2 times 2, 4, 5, 4. Well, he took reciprocal after, this is the reciprocal of that one. Then he knew that, oh, it seems very interesting. So you can see 2, 2, 4, 4, 6, 6, 8, 8, 10, 10, 12, 12. You continue even numbers on the top. On the bottom, we have odd numbers except the first term, 3, 3, 5, 5, 7, 7, 9, 9, 11, 11, 13, 13. So that is the estimate for pi over 2. If you want pi, just simply multiply by 2 on both sides. Pi 2 times this one. And if you want to estimate, you can do it up to anything you want. If you cut it here, it will give you estimate. It will give you the first few terms of pi. If you go the more terms you get actually as good as or better than Newton's estimate also. But this was done after Newton. That was done for pi over 2. That was Euler, and this is one of the main terms. Although Euler, when he did this one, he was not thinking about this one. His summation, actually the one that I showed you for the 1 over n squared, it has so many consequences. He was able to do many more series, and one of them is pi over 2, pi over 4. He could do many things actually, but he's pi over 2, this one. But here's what very strange. The credit goes to Euler because I like Euler now. He was the one who published it. But there was a guy by John Wallis, he was an English mathematician. He knew it actually in 1656 before Euler, but I don't think he showed how he knew this one, just the result appeared in his writing. So this is called now Euler-Wallis theorem. I mean, this is for both of them, but you can always argue who was the one. I think Wallis was the first one, but there wasn't any work how he found it. So you can find it on literature. Nobody knows how he just gave this one. This is all he gave. He gave it in this form, and they don't know how he was thinking. But it was done before Euler, so he couldn't be the only one that could be suspected is Euler knew the answer maybe ahead of time. I don't know. We don't have any evidence of that. The other thing that I will show is this is Francisco Witte. This guy actually has a different approach. He said I can use nested radicals to show pi or 2 over pi. And somehow he showed 2 over pi actually could be described by, first one is square root of 1/2, but the next one is square root, there is square root also under it, but 1/2 plus 1/2 times the square root of 1/2. Then the third one would be in the same fashion, the fourth one would be in the same fashion, and you continue to do that. If you really simplify them, this is better notation than what he has here. So square root over 2 for this one. Then for the next one, 2 square root over 2 over 2. The next one, 2. You can do on the next one, 3. This gives you a good approximation for 2 over pi. If you want pi, then what you have to do is 2 divided by whatever portion of this side if you want, to give you also a good estimate of pi. This is another one. This is infinite series, but you can get also up to any decimal accuracy you want to get pi from this series also. This one is due Vitus. And when I teach history of math, I always use this one because it's very easy to find estimates. It's fine, and it's easy to remember also, especially the second part is easier to remember the series. The series is easier to remember. So you can get up to any accuracy you want, decimal, by adding more terms, to the right, by adding more terms. So it will give you the estimate for pi. That is the Vite, and then the next one is actually, it has 3 names. Madhava was an Indian mathematician. This guy knew this series 14th century, and he didn't publish it though. They found it later in his work. So maybe there was no publication in India by then, or I don't know what the issue was. But in his writing, it was found later after those 2 guys announced it. Grigori also had in 1668, but he did not publish it also. So what happens was Leibniz came in, he published it in around 1676, he published it, this work. So most people give credit to Leibniz, but I think it should be given to the other 2. So now modern literatures, they give all of them credit. Some of them they say Madhava Leibniz, some of them they say Grigori Leibniz, but always Leibniz is included because he was the one who published it. This one is easier actually. What happens is they gave pi 4 times. Look the series. It's very easy to remember that series. 1 minus 1/3. You're using only odd numbers, reciprocal of odd numbers. 1 minus 1/3 plus 1/5 minus 1/7 plus 1. So you can do that. It's easy to remember. It seems very easy, and it's easy. But here's what is clever. I don't know if this is what they knew. Somebody knew this one, so they have to rely on Newton. That's the idea. This one wouldn't be a breakthrough because they knew how work from Newton, because they knew how to integrate now. They didn't know before Newton. Leibniz could claim it's his own work because he worked on calculus. So what they knew is this integral of 1 over 1 plus t squared is actually the arctan, the arctan tangent inverse. And if you express it in terms of series, that's what you get because there is series representation. In calculus, you guys do that by taking this one. So they knew that, and then they said, well, we can evaluate at x equals 1. Well, that gives you exactly what I have. And on the other side, you'll have pi over 4 because arctan at 1 is pi over 4. Arctangent at pi over 4. So that's what they did at 1 is pi over 4. So pi over 4 equals, and then they multiply by 4 to get pi. This one is also very good estimate. By adding more terms on the right side, you can get a better approximation of pi also. So, and there are many others actually in the literature. Still, people are trying to find better estimate. I don't know if you guys see, they know more than 1 billion digits of pi now using high-tech computers. Probably estimates are worthless now because we know how to do that. Especially these methods, if you have a good program, you can program them to calculate up to whatever accuracy you want it to be. Because we have already the formulas. So now people know, I think 1-something billion digits of pi are known. They have a record of one. Still, they are trying to search the next one. There are people actually devoting their life to find the next digit of pi. I'm not sure why. They do that in number theory. They do that in so we know so much now about pi, and we know it is irrational. It's not an irrational number, but it appears everywhere. All circular objects, or semicircular, or anything that has curve, pi is going to be involved somewhere. So it's very useful. So its history is also very useful for us because it gives us. In fact, what I didn't mention earlier in my first talk is that when Archimedes was doing, they they were relying on construction. They didn't have circles actually. They didn't know perfect circles. They were using compass and straight edge. They didn't have even marked edge by them. Everything they were thinking in terms of compass and straight edge without any mark. So they were trying to find the areas and other things. So they were struggling a lot. So their work is actually more interesting because they didn't have the tools that we have. In modern days, we have many other tools that we can manipulate this idea. We can use Leibniz series, Euler's, and others to find better approximation. That's why when we study history, the pi is probably one of the greatest theorems, not only, maybe the greatest one, which was done by Archimedes. As far as I'm concerned, I think it's the greatest one because I have no idea even how he knew the relationship. They knew there was a constant, and most of them before Archimedes, they were using area instead of circumference. They knew the area of a circle has something to do with some constant. Well, it was Archimedes he decided, well, I'm going to use circumference actually. I'm not going to follow what you guys are doing. So, and that was a breakthrough because nobody would think a circumference area would be the easier way to do. The area was to do. But for him, he used circumference and he shows them there is a constant and he gave the first estimate. Now, there are other, I mean, I don't know if you guys in school, when they teach you early in school, pi was estimated by a rational number always, by a rational number. For example, in school, grade school, they would say pi is 22/7 maybe, or they might have others. So those are a very good estimate. And then there are other estimates like continued fractions. We can show rational estimates of pi also, like continued fractions and others. But for this talk, I'll stop here. And if you guys have questions, you can ask me. But there are some references here. My favorite one is my textbook from my history of math. But then there are other sources here. So, if you guys have any questions in terms of pi from the first talk or from this talk, anything that you want to ask? No? Okay. And thank you for coming. And we will have third talk.